There is a photograph taken on Mars that NASA released without a single press conference. No announcement, no headline, just a raw image quietly uploaded to a public database, buried among thousands of others. That image shows something that, under any normal circumstances, would have triggered the biggest scientific announcement in human history. And yet, for years, almost nobody talked about it. This is not a conspiracy theory. This is a pattern, a slow, careful, deliberate pattern of discovery, hesitation, and silence that stretches back over 20 years. And once you see it laid out from the beginning, you will never look at the Mars program the same way again. Let's start at the beginning. Not with the rovers, not with the orbiters. With a scientist sitting in a laboratory in 1996, staring at a rock. The rock had a name, ALH84001. It was a meteorite found in Antarctica in 1984. But geochemical analysis confirmed it had originated on Mars, blasted off the planet by a massive impact billions of years ago, and eventually captured by Earth's gravity. What the scientists found inside that rock stopped the entire team cold. Tiny, elongated structures, nanometer-scale formations embedded in the mineral matrix of the rock that bore a striking resemblance to fossilized microbial life. On August 7, 1996, President Bill Clinton stood in front of the White House and addressed the nation. He called it one of the most stunning insights into our universe that science has ever uncovered. NASA held a press conference. The world paid attention. Then the scientists started arguing, hard. Over the following years, researchers challenged every piece of evidence. The structures were too small to be bacteria, some said. The chemical signatures could have come from contamination during the rock's long journey through space. The minerals could have formed through purely geological processes without any biology involved. By the early 2000s, the mainstream scientific community had quietly moved on. The rock was filed away. The excitement faded. But here is what almost nobody mentions. The scientists who originally made that discovery never withdrew their claim. They kept publishing. They kept refining their analysis. And in 2009, the lead researcher published a comprehensive follow-up paper concluding that the biological explanation remained the most consistent with all available evidence. NASA said nothing publicly. No press release. No updated statement. The 1996 story was simply allowed to die in the public consciousness. While the underlying scientific debate continued in academic journals, almost nobody reads. That pattern, discovery, brief acknowledgement, quiet retreat, is the thread that runs through this entire story. Now let's talk about water. Because water is where things start getting genuinely uncomfortable. For most of the 20th century, Mars was considered bone dry. The atmosphere is thin. The surface temperature averages around -60 degrees Celsius, and any liquid water exposed to that environment would freeze or evaporate almost instantly. That was the accepted picture, and it was wrong. In 2000, the Mars Global Surveyor spacecraft captured images of gullies, narrow channels carved into steep crater walls, and hillsides that looked freshly formed, not billions of years old, not millions. The morphology of these gullies matched erosion patterns created by flowing liquid water on Earth. The team that analyzed the images published their findings. The response from NASA was careful and measured. The agency said the gullies were intriguing, but that liquid water was not necessarily the explanation. Dry granular flows, carbon dioxide, frost, or other mechanisms could potentially account for the features. That statement was technically accurate, but here is what the public was not told clearly. The researchers who found those gullies believed, based on the evidence available to them, that the most straightforward explanation was recent liquid water activity. Not ancient, recent, possibly ongoing. Over the next several years, the Mars Global Surveyor continued imaging the same gullies, and in 2006, a follow-up study found something extraordinary. New deposits had appeared inside gullies that had been empty in images taken just a few years earlier. Bright, light-toned material sitting exactly where you would expect it if water had flowed, deposited sediment, and then evaporated or The researchers were careful in how they stated their conclusions, but the implication was clear. Something had moved through those gullies within the last few years, something that left bright mineral deposits, something that behaved like water. NASA's public communication at the time emphasized uncertainty. Every press release came wrapped in qualifiers. The word possible appeared constantly. The word confirmed did not. Meanwhile, inside the research community, the evidence for recent water activity on Mars was becoming harder and harder to dismiss. Then came the methane dot in 2004. 3 independent research teams, one using Earth-based telescopes, one using the European Space Agency's Mars Express orbiter, and one using NASA's own infrared telescope facility, all detected methane in Mars's atmosphere. This should have been a much bigger story than it was. Methane is unstable in the Martian atmosphere. Ultraviolet radiation from the sun breaks it down relatively quickly on a geological timescale. The methane present today could not have been there for more than a few hundred years, which means it is being actively replenished. There are 2 main ways to produce methane: geological processes involving water reacting with certain rock types, a process called serpentinization, and biological processes, living organisms, producing methane as a metabolic byproduct. On Earth, the vast majority of atmospheric methane comes from biology. The detection of methane on Mars meant that something, right now, in the present day, is actively producing a gas that life on Earth produces in enormous quantities, and whatever is producing it is doing so continuously. NASA acknowledged the detection. The agency explained both the geological and biological possibilities, and then, for years, the public conversation around Martian methane essentially stalled. What happened behind the scenes was far more interesting. The Curiosity rover, which landed in Gale Crater in August 2012, was specifically equipped with an instrument called the Sample Analysis at Mars System, designed in part to measure methane concentrations directly from the Martian surface. In 2014, the Curiosity team reported something remarkable. Background methane levels in Gale Crater were low, but over the course of a 2-month period in late 2013, the rover measured methane spikes that were 10 times higher than the background level. The spikes appeared, persisted for a short time, and then disappeared. The pattern was consistent with a nearby episodic source, something releasing bursts of methane periodically. The paper was published. The findings were real. And then the scientific community spent the next several years arguing about whether Curiosity's instruments were reliable enough to trust the measurements. Meanwhile, the European Space Agency's Trace Gas Orbiter arrived at Mars in 2016, specifically to study atmospheric gases, including methane, in unprecedented detail. Its results, published in 2019, showed no methane detectable at the level the Trace Gas Orbiter was capable of measuring. This created a direct contradiction. Curiosity was detecting methane from the surface. The Trace Gas Orbiter could not confirm it from orbit. The scientific debate that followed was genuinely complex. Some researchers proposed that methane near the surface might be destroyed before it can mix into the upper atmosphere. Others suggested Curiosity's measurements might be influenced by the rover's own chemistry. But here is the thing that gets lost in that technical debate. Nobody has explained where the methane Curiosity detected actually came from. The source has never been identified. The contradiction between the surface measurements and the orbital measurements has never been resolved. And Mars still has methane in its atmosphere. That fact has not changed. Now let's talk about the thing that may be the most significant discovery in the history of Mars exploration, one that has been known for nearly 2 decades and has never received the public attention it deserves. Recurring slope, linear. They are dark streaks that appear on Martian slopes during the warmer months, grow longer as temperatures rise, and then fade or disappear as temperatures drop. They move like liquid. They behave like liquid. They appear exactly where and when you would expect liquid water to appear if liquid water existed on Mars today. The Mars Reconnaissance Orbiter first captured detailed images of these features in the mid-2000s. Researchers spent years analyzing them before publishing the initial findings. When the paper came out in 2011, the language was cautious. The features were described as consistent with briny water flows, salt water, which has a lower freezing point than pure water and could potentially remain liquid at Martian surface temperatures. The public reaction was significant. This was, after all, evidence of potentially flowing water on Mars in the present day. NASA's response was, once again, careful, possible, consistent with, not confirmed. Over the following years, the debate intensified. The features appeared on hundreds of slopes across the planet. They showed seasonal behavior perfectly aligned with what liquid water would do. The spectral signatures, the way they reflected different wavelengths of light, matched hydrated salts. In 2015, NASA held a press conference and announced that liquid water flows had been confirmed on present-day Mars. It was a major headline. It briefly dominated global news coverage, and then, quietly, the scientific community walked it back. Subsequent analysis suggested that the dark streaks might not require liquid water at all. Dry granular flows of salts, triggered by temperature changes, could potentially produce similar features. The hydrated salt signatures might be picking up material from the surrounding terrain rather than from the streaks themselves. By 2019, the dominant scientific position had shifted. The recurring slope linea were no longer described as probable water flows. They were described as uncertain, possible water, possible dry flow, origin unknown. But here is what is critical to understand about that shift. The features are still there. They still appear every Martian spring. They still grow and fade with temperature in ways that precisely match water behavior. No alternative explanation has been fully confirmed either. What changed was not the evidence. What changed was the willingness to make a strong claim based on it. And this is the pattern. This is what has been happening for 20 years across every major Mars discovery. Evidence appears. Researchers make cautious but significant claims. The scientific community debates. Alternative explanations are proposed. The original claim is softened or abandoned publicly, even when the underlying evidence has not actually been refuted. The result is a situation where the public believes Mars has been thoroughly studied and found to be empty and lifeless, while the actual scientific literature contains decades of unresolved findings that point in a very different direction. Let's go further. Let's talk about what the Viking landers found in 1976, because this is where the story gets its deepest roots. Viking 1 and Viking 2 touched down on Mars in the summer of 1976. They were equipped with a suite of biology experiments, specifically designed to test for microbial life in the Martian soil. One of those experiments was called the labeled release experiment. It worked like this. Martian soil was introduced to a nutrient solution laced with radioactive carbon. If living organisms were present and consuming the nutrients, they would release radioactive carbon dioxide as a metabolic byproduct, which detectors would then measure. The results came back positive. The soil consumed the nutrients. Radioactive gas was released. The pattern matched what you would expect from microbial metabolism. The principal investigator of the labeled release experiment, a scientist named Gilbert Levin, spent the rest of his career arguing that his experiment had detected life. He published papers, he gave talks, he made the case repeatedly and methodically. NASA's official position, based primarily on the results of a companion instrument called the gas chromatograph mass spectrometer, was that no organic molecules had been detected in the Martian soil, and without organics, there could be no life. The GCMS results were considered definitive. The biology experiment results were classified as a chemical false positive, caused by highly reactive compounds in the soil called perchlorates, reacting with the nutrient solution and mimicking the signature of biological activity. That explanation became the standard answer for the next several decades. But in 2008, the Phoenix lander confirmed something that changed the interpretation of the Viking results entirely. Phoenix detected perchlorates in the Martian soil, the same reactive compounds NASA had proposed as the non-biological explanation for the Viking results. This was treated as a confirmation that the Viking false positive hypothesis was correct, except it was not that simple, and several researchers pointed this out immediately. The GCMS instrument on the Viking landers worked by heating Martian soil to extremely high temperatures to vaporize organic compounds for detection. If the soil contained perchlorates, which we now know it does, heating it would cause the perchlorates to combust any organic molecules present, destroying them before they could be detected. In other words, the instrument that was supposed to confirm the absence of organics was operating in a way that would have destroyed organics, even if they were present. A reanalysis published in 2010 suggested that the Viking GCMS may have detected trace organics that were masked by the perchlorate combustion process. What looked like a negative result may have actually been a masked positive. Levin argued consistently that this reanalysis vindicated his original findings, that Viking had, in fact, detected life, and that the instrument intended to confirm it had inadvertently destroyed the evidence it was looking for. NASA has never formally revised its official position on the Viking biology experiments. Now let's jump forward, because the story gets significantly more interesting with Curiosity. When Curiosity landed in Gale Crater in 2012, one of its primary objectives was to determine whether Mars had ever been habitable, capable of supporting life. Not whether life existed, but whether the conditions were ever right. Within its first year of operation, Curiosity found the answer, and the answer was yes. The rover drove into an ancient stream and found rounded pebbles, the kind that only form when water flows over rocks for extended periods. The chemistry of the surrounding rock indicated a neutral pH environment, moderate salinity, and the presence of chemical energy sources that microbes on Earth routinely use for metabolism. The scientists were unambiguous about this finding. Gale Crater had once been habitable. It had contained a lake environment that could have supported microbial life for potentially millions of years. This was a genuinely significant result. The habitability of ancient Mars was no longer theoretical. It was confirmed by direct measurement. But then curiosity kept going, and the findings got more complicated. In 2018, the mission reported the detection of complex organic molecules preserved in 3.5 billion-year-old sedimentary rock inside Gale Crater. These were not simple carbon compounds. They were thiophanes, benzene, toluene, and other relatively complex organic structures. The team was careful to note that organic molecules can have both biological and non-biological origins. Meteorites carry organic compounds to planetary surfaces regularly. The presence of organics alone does not indicate life, but the preservation of these molecules over 3.5 billion years in surface rock on a planet bombarded by ultraviolet radiation was itself remarkable. It suggested the rock had protected the compounds from destruction, which has implications for whether biological material might also be preserved in similar environments. Then, in 2021, Curiosity detected its highest single methane spike to date, 21 parts per billion by volume. The spike appeared and disappeared within a single day. No source was identified. No explanation was confirmed. The detection was real. The origin remains unknown. In 2018, a groundbreaking discovery was announced, this time not on the surface of Mars, but beneath it. The European Space Agency's Marsis radar, aboard the Mars Express orbiter, had been scanning beneath the south polar ice cap of Mars for over a decade. In data collected between 2012 and 2015, researchers identified a radar reflection pattern that matched the signature produced by liquid water, not ice, liquid water. A subsurface lake approximately 20 kilometers wide, sitting about 1.5 kilometers beneath the polar ice, kept liquid by a combination of pressure, salt content, and possibly geothermal heat. The announcement made global headlines. A subglacial lake on Mars, directly analogous to the subglacial lakes of Antarctica on Earth, several of which harbor microbial life, despite being isolated from the surface for millions of years. Then, in 2021, follow-up analysis identified not one but 3 additional radar reflections with similar signatures surrounding the first lake, suggesting a system of subglacial water bodies rather than a single isolated feature. And then the controversy began. Other researchers began reanalyzing the Marsis data and questioning whether the radar signatures truly indicated liquid water. Some proposed that the reflections could be produced by specific types of clay minerals or volcanic material rather than liquid. The debate is ongoing, but the critical point is this: the data is the same data. The radar reflections are real. What is being argued is the interpretation. And in that interpretive uncertainty, the story has once again quietly retreated from public attention. The subglacial lakes of Mars are no longer a regular topic of mainstream science coverage. The finding that once generated global headlines has been softened into a footnote, but the radar reflections are still there. Now let's talk about something that almost nobody outside the specialist community knows about. In 2020, a team analyzing data from the MAVEN orbiter published findings on hydrogen in the Martian atmosphere. Their analysis found a seasonal variation in hydrogen concentrations that correlated with known methane variations. The correlation was significant because hydrogen, like methane, can be produced both geologically and biologically, and the fact that both gases were varying in similar seasonal patterns suggested a common source. The paper was published, the findings were presented at a conference. And then, essentially nothing happened. No follow-up mission was designed to investigate the hydrogen-methane correlation. No press release from NASA drew attention to the paper. The finding sits in the published literature, accessible to anyone who knows to look for it, effectively invisible to everyone else. This is not suppression in the dramatic sense. Nobody confiscated the paper. Nobody threatened the researchers. The findings are publicly available. But public availability and public knowledge are not the same thing. And the gap between what the scientific literature contains about Mars and what the general public understands about Mars is enormous. In 2022, NASA's InSight lander recorded the largest seismic event ever detected on another planet, a significant Marsquake that sent waves propagating through the planet's interior. The analysis of those waves revealed something unexpected. The Martian mantle appears to contain regions of unexpected composition, layers that do not match the models geologists had built based on decades of orbital data. One interpretation is that Mars's interior is more geologically complex and potentially more active than previously believed, which has direct implications for whether geothermal heat could be sustaining liquid water environments in the subsurface, which has direct implications for habitability. InSight's mission ended in December 2022, when dust accumulation on its solar panels reduced power below operating levels. The data it collected is still being analyzed. No follow-up lander or seismometer network mission has been approved. We placed one seismometer on one location on an entire planet for less than 4 years, and drew broad conclusions about Mars's interior from that single data point. The scientific community knows this is insufficient. A network of seismometers distributed across Mars would transform our understanding of the planet's interior and its geothermal activity. No such network has been funded or scheduled. Let's talk about Perseverance, which is operating on Mars right now. Perseverance landed in Jezero crater in February 2021. Jezero is an ancient river delta, a site specifically chosen because river deltas on Earth are among the most productive environments for preserving biosignatures. If life ever existed on Mars, a river delta is among the best places to look for its preserved traces. The rover has been drilling rock cores and sealing them in sample tubes for eventual return to Earth. This Mars sample return mission is the linchpin of NASA's entire search for life strategy. The idea being that the instruments needed to definitively determine whether a sample contains biosignatures are too large and complex to send to Mars, so the samples must come here instead. The first samples collected by Perseverance have already been described as extraordinarily interesting by the mission science team. Organic molecules have been detected in multiple samples. Minerals associated with water alteration are present. The preservation conditions appear excellent, but those samples are sitting in tubes on the Martian surface right now, and the Mars sample return mission, the mission designed to bring them back, is in serious trouble. An independent review of the mission architecture found it massively over budget, years behind schedule, and technically more complex than any uncrewed mission ever attempted. The estimated cost had ballooned to somewhere between $8 and $11 billion. The earliest possible return date had slipped to the late 2030s at minimum. As of now, the samples Perseverance has collected, potentially the most scientifically significant planetary science samples in human history, are sitting on Mars with no confirmed plan to retrieve them. And this is perhaps the most important part of this entire story. Not the individual discoveries, not the methane, not the water streaks, not the biology experiments, not the subglacial lakes. The most important part is what has not happened. After every single one of these findings, the scientifically obvious next step would have been to design and launch a targeted follow-up mission directly, addressing the open question. It never happened. Not once. Not for any of these discoveries. Instead, every follow-up has been a general-purpose mission with multiple scientific objectives and no specific mandate to resolve the question of whether Mars harbors or harbored life. There are practical explanations for this. Space missions take decades to design and launch. Budgets are limited. Scientific committees prioritize conservatively. The political will to make Mars life the explicit target of a billion-dollar mission does not exist. But there is another way to look at it. If you wanted to study Mars indefinitely, without ever definitively answering the question of life, the strategy you would use looks almost exactly like the strategy that has been used for the past 20 years. Send general-purpose rovers. Collect data that is intriguing but not conclusive. Debate interpretations in the literature. Underfund the follow-up missions that would provide definitive answers. Keep the question open. This is not a claim that anyone is deliberately doing this. The boring explanation, bureaucratic caution, budget constraints, scientific conservatism, institutional risk aversion, accounts for everything observed without requiring any hidden agenda. But the outcome is the same regardless of intent. We have been circling the question of life on Mars for 5 decades. We have gathered the amounts of evidence that the question deserves to be answered, and we have consistently stopped just short of the moment that would force a definitive answer. Gilbert Levin, the Viking scientist who spent his career arguing his experiment had detected life, died in 2021. He never received a formal revision of NASA's position on his results. The meteorite ALH84001 is still in a laboratory. The scientists who first described its possible biosignatures still believe the biological hypothesis is the most consistent with the evidence. Nobody has definitively proven them wrong. The methane on Mars is still there. The source is still unknown. The subglacial radar reflections are still there. The interpretation is still debated. The organic molecules in Gale crater sediment are still there. Their origin is still uncertain. The recurring slope lineae still appear every Martian spring. Their mechanism is still disputed. The sample tubes Perseverance has filled in Jezero crater are still sitting on the Martian surface with no confirmed retrieval mission. And the question that has driven the entire Mars exploration program since 1976 remains officially unanswered. What is on Mars? Not what was on Mars billions of years ago. Not what theoretical models suggest might be possible. What is there right now, in the present day, in the subsurface environments where liquid water may exist, in the ancient sediment where organic molecules have been preserved, in whatever is producing the methane that curiosity detected and no one has explained. We do not know. And we have spent 20 years generating evidence that should have driven us urgently toward finding out, while instead moving slowly, cautiously, and always just short of the answer. Maybe the next mission will be different. Maybe the Mars sample return will eventually get funded, and the samples will come back, and the instruments here on Earth will give us the answer one way or the other. Maybe what is in those sample tubes will change everything. Or maybe we will spend another 20 years debating what the results mean. Mars may be something we have been afraid to find out. Thanks for watching. See you in the next one.